good. We'll sort of increasingly get a little more rigorous with our proofs of the Arnold conjecture. Right now I'm going to get a little less rigorous because I don't really want to introduce all of the symplectic field theory setup. But I want to tell you how one can somewhat easier rewrite these fantastically complicated compactified moduli spaces if you assume that you know symplectic field theory compactified moduli spaces. So, and that might be the motivation for looking at that, which I don't think I'm going to do. The compactness theorem for symplectic field theory has been published for quite a while. So the sort of description of the moduli spaces is there. We expect any time now a description in terms of polyfolds, which is why I like to get myself into that world. So, all right, our fantastic new PSS spaces now need to use broken Morse trajectories and bubble trees and strings of broken flirt trajectories. That look pretty atrocious, but we can rewrite it as a simple fiber product just in terms of this compactified Morse trajectory space and an SFT space. And I'm going to write n now because I'm running out of curly m's, which then will just depend on the end periodic orbit gamma. So, and that's, big surprise, the n is going to be all the gray stuff and the Morse should be just the green stuff. And so there's going to be evaluation maps on both, and we'll, somewhere, this matching will be encoded by evaluation maps and a fiber product. So, and then obviously we're going to do exactly the same thing with the SSP map, except then there's going to be an n minus. So I need to tell you what this n is. So I'm not going to tell you what n bar is. I'm just going to tell you that n bar is the SFT, not compactation of the following set, where the following set could be empty and this could be non-empty. So it's not a compactification in the old sense. It is a compact set that in particular contains this. So n plus of gamma is, well, you'd say, well, silly, now you're just going to write the old equation back, holomorphic planes with the perturbed d-bar equation, but we're going to do that in a very complicated way. So I'm going to write that in terms of holomorphic planes in C times m. So I want to think of the graph of my holomorphic planes that sits in C times m. The beauty is that when I talk about the map this way, I can push all the perturbation into my J. So it's going to be an unperturbed holomorphic curve equation. I'm just going to need to tell you which one that is. And then, well, I would like to make sure that this is actually covers C, the identity, so that I get, really just the graph of a map and not a multi-valued map. So I'm going to need to somehow fix U hat, say in terms of even homology classes, I think would be fine to say it's the identity times some homology class A of maps from C to M, and for that A I can then say what the energy is. Oops. Alright, so luckily I'd written my energy always in terms of some kind of homology invariant. So that makes more sense, because if I was trying to talk about somehow integral du hat squared, right, that is the basic SFT problem, is if I'm thinking u hat is going to be the identity on this C parameter, this is going to have infinite energy. And so I just want somehow the energy of the M part here. So that's what I get here. This is not, there is a neater way of, really I should turn this into some discussion of Hopper energy, which I'm not going to do. And I'm also not really going to start talking about what the translation of the sort of limits at C equal to infinity is. What happens here now is, let's see, the periodic orbit gamma in M that I want to limit to ends up being a rib orbit in the end of this side. So this here actually, so when I do C plus, is a symplectic cobordism with positive end, that's S1 times M. That's a contact manifold, or sort of contact enough for symplectic field theory to work. And then the graph of my rate orbit gamma, right, sits over S1 times M. Sorry, the graph of my Hamiltonian orbit. And in S1 times M, then there is a contact structure or contact form that makes that the graph of the Hamiltonian orbit a rate orbit. And so then over rate orbits there are trivial cylinders that then at punctures these U hats are sort of asymptotic towards that whole cylinder. So that's the whole fluff. Really, so what am I going to say? U hat in the neighborhood of infinity now. So that's the puncture in C, is somehow asymptotic to, well, it goes towards infinity in that C also. So I'm just going to write somehow infinity times gamma. You should think that really secretly there's the graph of gamma that sort of converges to. Right. And that's not quite the end of the story, right? Because if I had that, then I would, I could shift all of these maps, however, within C. So I do want to now, since, well, I haven't said that what the J hat is exactly, but I do need to quotient by the automorphisms of C, I believe it turns out. Is that right? Oh boy, I think so. Let's think about that in a second. I'm a little confused right now. Thinking that I want to make this map the identity on C by a shift. But let's see what my J hat is. So as a map to C, I would just like it to be little J holomorphic. So this is the first row here is on the tangent space to C. And then on the tangent space to M, I would like to introduce my perturbation. So within Tm, I should have the J, and, well, here this pairs the directions on C with the directions on M, which allows me to write this kind of Hamiltonian vector field down. Right, yes. And so the perturbation is, the J is now going to depend on the point in this C and in M. the domain-dependent perturbation sort of becomes a J that depends, on both of these parameters, but not on the domain anymore. So. So in particular, I didn't have to tell you at which point in C I am when I write down this J hat, which and that means I now actually do have an action of the automorphism group on C that keeps this. So I need to quotient by that. So that's essentially just means now, since I asked the first component of U hat to be homologic to the identity and holomorphic, it just means it is actually the identity. So that U hat really just is the graph of my map from C to M. It's a silly way of saying, perturbed holomorphic planes in M. But here's the SFT gray box, which I already said. The nice thing is that there is a general setup when you have something called a symplectic cobordism. Here in the plus case, it goes sort of from the empty set to S1 times M. So it has a positive end now, that's R plus times S1 times M. It's just sort of polar coordinates in C. And then the general compactation wisdom is that now, since your target of your symplectic manifolds, so your target of your holomorphic curves is non-compact, there's sort of a new effect that can happen. So it's not quite breaking, it's not bubbling, it's no gradient doesn't blow up. It's also not energy running off to infinity in the domain. It's parts of the curve running out to infinity in the target. So in particular, they can run off this end, right, to stuff that sort of sits on in R plus. If it runs off to infinity, it sits in a part of the symplectic manifold that then looks like R times S1 times M. And so that's what the breaking in Floer theory becomes. It's sort of this running off in the target. And so the key word here is then buildings. So your, what you really think of is, this is sort of your C times M. That's the first level, and there's a bunch of levels above there that are these cylinder times M. And which level your part of a curve ends up in depends on how fast the elevator goes up, or how fast the divergence goes. So you can imagine different parts of interesting curve going off to infinity at different speeds, and so in the limit you want to somehow separate them out. So but there's always just going to be one level in C times M, because there's always just going to be somehow one point where maybe your point 0 sits, and you can always look at, and that's where something interesting with your J hat happens. And so, you nail that one down. That's your sort of first level. And in that world, so then, in each of the levels you can have bubbling also. So nodal curves can appear. So you get, trees of spheres on your curves that sit in every level. And you could worry whether you can pick up genus. In general symplectic field theory, your curves can now have interesting genus. What avoids that in our setting is that we're asking for a very simple homology class here. So there won't be genus. Right. And now it's also somehow easier to talk about the symmetry between PSS and SSP. It's what we change when we go to the SSP moduli space is we just declare the infinity at C as a negative end. So give it coordinates r minus, and then you just turn this thing upside down, so you have the top level being C times M, and you can get levels below that. Right. Oh yeah, so the piece obviously, right? So this end here, you see here, asymptotic here and asymptotic there. And so then you get to add sort of copies of the end in your buildings. Phew. So that was a sort of 2-minute summary of symplectic field theory moduli spaces. So for now they're just convenient because we don't have to talk about all these perturbations anymore. They just sit in the J.
But symplectic cobordism is always like blowing up or blowing down or something?
No. So generally a symplectic cobordism is a symplectic manifold that has positive and negative ends that look like R plus and minus times a contact manifold. So, you can imagine that, it doesn't matter what it doesn't need to be a product, it just needs to be something that you can count holomorphic curves in, and that somehow whose non-compactness is controlled in such a way that, when curves run out here, you can control them in some sort of simple pieces.
So I mean, for the level set, maybe quotient by S1 action, the reduced bits are related by blowing out?
I mean, here, yes, you have an S1 action on the sort of infinity, but in general you don't. So it could be in any contact manifold. Like S3, for example. Well, S3 has an S1 actually, but it doesn't.
So there's no explicit description of how the level contact manifolds are related.
No. Oh, so in general, there's in general, this bit here is a contact manifold.
But in the middle,
and then you have sort of the symplectic cobordism, and the levels are R times my contact manifold, which is known as the symplectization of a contact manifold.
Also, you mean you only know the ends, how the ends look like in between the
Yes, yes. So, well, the complication, however, sits here, just in this one piece. That's the complicated symplectic cobordism, and then and I know what the end looks like. Good. All right. So that was PSS and SSP, and now, of course, we would like to do my other moduli spaces in the same way. Right. I'd like to make that composition homotopic to my nice map I. So here's those guys again, neatly written, and now what do we do with H? Right, so that was this atrocious long union where I allow myself perturbations of finite length support R, and when they go to infinite length, I expect things to break some number of times. Right? And so now you can imagine that what's going to happen is there's going to be some breaking into levels. So one way or the other. somehow levels of an SFT building. So the question is, how do we describe that? With a cheat sheet, of course. Right. So I would like that to again be a fiber product. Right, and now I have Morse trajectories on beginning and end, so it's probably going to be a fiber product at beginning and end Morse trajectories. Some SFT moduli space, and that's now one that comes from something we like to call next stretching, and the other Morse moduli space. Oh, I cheat. Oh, okay, hold on. Sorry, I need to go back. And right, so the one thing I didn't tell you was how my evaluation map actually, what becomes of that. Right, because that's a little obscure. I'm quotienting by the entire automorphism action of C here. I'm not fixing 0. Right? So I can't quite evaluate U hat at 0 anymore. Right? But what I can do, so really secretly this is a map modulo reparameterizations. But what I can do is I can take its image, right? So the image is well defined, and intersect that with the hypersurface 0 times m. And because I'm in the homology class identity times A, I'm expecting only one intersection point, and that's going to be my new evaluation map to M.
So what's the C plus?
C, oh, well, that's just saying C with a positive end. I'm thinking of C as a symplectic cobordism between the empty set and the circle, where it goes from the empty set to the circle. Right, and for n minus, I'm thinking of it as a cobordism from the circle to the empty set. All right, so evaluation map now becomes some sort of intersection. And so, as such, I'm hopefully not going to have to worry about that when I talk about stretching SFT spaces. So, right. And I already gave that away. So n bar stretch now should be some compactation again. And that comes from the idea in symplectic field theory that not only can you look at all these buildings, you can also force, you can take 2 levels, or you can take 1 level of your building and sort of stretch it. And then eventually it's forced to become a multi-level building. So let me try to write this out. So right, and again, I'm only going to tell you what the sort of nice part is, something that I would hope to be a dense subset, but in general may not be even a non-empty subset. So again, I'm not going to really say what I get at R equal to infinity. I'm going to let R be finite. Right? And in those cases, we wanted perturbed holomorphic spheres. We play the same game now. I'm thinking of them as they're mapped to the graphs. So parameterized by P1. And then the change in the perturbations now just becomes a change in the J. So they're all strictly holomorphic, and I need to play the same game again and make sure that it's really just sort of on P1. This is just the identity map, so I'm going to force it to be identity times some class of maps from P1 to M where that second class has finite energy. Right. And now this here is actually a symplectic manifold that's compact. So, right, no issues around, well, I could have written energy finite even for U hat, but since we want to stretch it, that's not a good idea. And again, I now quotient by the entire Möbius group. But I can still do evaluations here. Simply by evaluating by intersection. By the image intersected with 0 or infinity times M. And then, of course, I project that to M. So, evaluations are still intersections. And now, right, so my whole stretching happens in the J hat. That changes. So, sort of as a symplectic cobordism, what happens here is that I have P1 times M with an almost complex structure J hat. Right, but that also has a symplectic structure, and together that gives me a metric that now depends on R. And in that metric, I'm stretching some part of my symplectic manifold pretty brutally. So if I look at a little annulus in the middle here, in that metric I can measure the length of that, and that is going to be its length, R. So that's the geometric meaning now of degenerating the J. It's, there's a longer and longer, well, annulus times M on which sort of my J is going to be in standard form and translation invariant. That's exactly the area where we used to have the sort of translation invariant Hamiltonian perturbation. And that's where I'm picking up a lot of length in this metric. So then as a symplectic cobordism with this metric, it actually converges to sort of a broken symplectic cobordism, namely the one where, well, really I break along the circles in P1. M is always sort of fight over this and pretty finite length or finite volume for each of the metrics. So I break my P1 into two planes, namely C plus and C minus. And the resulting Hamiltonian perturbations worked very nicely to give you the PSS and the SSP, and that means I'm getting the resulting sort of PSS J's here on the broken stuff. So that's again a silly way of reformulating that whole PDE degeneration. It's useful because people have written down the compactness statement for us. So let's again, Hofer et al. Did this whole setup not because they were thinking about the Arnold conjecture. Really, they were thinking about calculating Gromov-Witten invariance for a compact symplectic manifold like that one by pulling it apart and then hopefully being able to calculate the invariance for the two parts easier. that's why it's called field theory. Always, trying to calculate things by sort of cutting the complicated topological things into simpler topological pieces at the expense of introducing boundary. And this has sort of boundary at infinity. So, and again, just sort of as in the breaking argument that I made before, right? I said, well, when you make this longer and longer, you force it to break once at least, but then energy could concentrate in such a way that you're seeing several breakings. The same thing happens here. As R goes to infinity, you force your curve into these two bits, but there could be extra buildings, extra levels in between that then are this are invariant pieces of the ends. S1 times m is the positive end of this one, it's the negative end of that one. So I guess pictures very intuitively. That one, right, where this one has a positive end, that's R plus times S1 times m, and this one has this negative end. So there's your story. Right. So that's the interesting PSS moduli space, and then from this one we can again take the R equal to 0 part where the perturbation is gone. Which means in this world I'm fixing my J, I'm not forcing things apart. And now that's maybe, a good reason to understand why there's now no breaking, because my symplectic manifold has no non-compactness and I'm not degenerating my J. So the only thing that happens is nodes. Right? So we're going to see this piece where there's a single level of nodal curves, except there's still one that's unique in that it's sort of secretly, that's the parameterized one. So that comes from making this set up again as, graph of a map, and then, one of these, then you have to sphere compactify that. And that's going to be extra gray stuff that sits on the U hat. So this blue thing here will be the image of the limit U hat. And then there'll be gradient, blow up of the gradient in U hat can happen. And that's when you rescale to see the other spheres. So bubbling in SFT still looks exactly the same way. Right, just for completeness, I can write this now also as nice fiber product right with my two Morse moduli spaces. And I'm just taking the next stretching SFT moduli space, but fixed at neck unstretched with R equal to 0. And two fiber products. So, goal is that at some point today you'll understand why I keep being so excited about being able to write things as fiber products. Not just because they start looking somewhat simpler now. So, all right. Now that we have, first of all, I'm excited because now I can actually get all my moduli spaces in the column of a table. Right? So if we now assume that we know what these n bar SFT spaces are, so and whenever you see an n, now you think holomorphic curves in some compact or non-compact symplectic manifolds. And whenever you see m bar, those are simply Morse trajectory spaces. Right. The beauty of the Morse trajectory spaces is that they're already smooth, compact manifolds with boundary and corners. So then we can expect boundary phenomena, and we can try to sort of write down equations for what my what the virtual dimension is. People like to call it virtual dimension or expected dimension. If these moduli spaces were cut out transversely or are regular, then that should be the dimension. So personally, I like to call this Fredholm index. If you actually write your moduli space as a zero set of a Fredholm section. The problem with that is that, right, we did that for this SFT moduli space, so the n bar. However, we also quotiented. Whoa. That didn't work. All right. So we quotiented by C in that case. So, Fredholm index, good and great, but you do have to subtract the dimension of that automorphism group. Because really secretly you want to write down your d bar operator on a space of maps modulo C. Right? Except that, time and time again, you can't quotient smoothly by reparameterization. So I can't talk about the index of d bar when restricted to the quotient space. I can talk about it when restricted to a local slice. That's what we did to get our local Fredholm descriptions. So, bottom line is there is some kind of Fredholm index just for the SFT problem here. And then I'm writing down an extra finite dimensional equation that just involves a evaluation map from this space. And the condition is that it lies on, the compactification of the unstable manifold here. So that's just finite amount of data that I'm asking for, so I'm just subtracting that dimension. Right, and I've suggestively called the p's now always p minus np plus. Because now I can, so I can play the same game with SSP. There's a Fredholm index of the d bar on this SFT space. Well, I should probably say d bar j hat. Minus the automorphisms I quotient by, minus the condition, which now comes from the stable manifold. Similarly for I is better because I just have a d bar operator, and now I have two incidence conditions, so I'm subtracting both of them. Right. And obviously I should do the same thing for my homotopy, except in my homotopy I also have this parameter R. So really I have a family of d bar operators. So for a single d bar operator I have an index there, and maybe I'm adding one for that R parameter. Not really going to do much with the identification of the Fredholm index here, but it's sort of a good first exercise to see what the description as a fiber product does for you. Right, in some sense this was already somehow the argument that if the ends are cut out as Fredholm sections, then the bigger spaces are cut out as Fredholm sections, because I'm just adding some finite conditions. So this was secretly a calculation of Fredholm indices. Good. And let's see. Right. So boundary. Right. So if my moduli spaces are nice and regular, I expect them to have boundary and corners. And where is that going to come from? Right? Well, you look again at the fiber product. It's a fiber product over a closed manifold. So you expect the boundary to either come from one of the factors. The first factor just has Morse breaking. And the second factor has, well, whatever SFT does. Right? So SFT has different levels of buildings. That looks like codimension 1. It's sort of nicely stacked. So indeed, different numbers of building levels will give you more and more boundary strata. And then the other thing that was in SFT compactification that we sort of didn't quite talk about is the nodal curves. So the mantra here is that you can have nodal curves in every level, but we expect them that they are codimension 2 phenomena. Not only codimension 2, but actually interior. So you expect your moduli space to look something like this, with your nodal curve somehow just being a point there. And it might not be clear how to extend a smooth structure across it, but that here clearly, because it could have a cone metric or something, but it clearly has a structure of a topological manifold. As I drew it here, in general, if you read the McDuff-Solomon book, they sort of make this rigorous in terms of pseudocycles. There's sort of something missing, but it's so small that it doesn't affect the sort of having a well-defined cycle that you can integrate things over questions.
So even if you had like a whole bubble tree, it's still just one.
Right. This could be an entire humongous bubble tree. It's just for every node you're going to have more and more codimension. So a bubble tree with 25 nodes, I'm expecting to only see in codimension 50.
Okay.
But in the end, when we do polyfolds, it's going to be a totally fine interior point, and any one manifold, is allowed to go through there. I'm just not even going to care. It's interior point for me.
We're going to get to polyfolds?
Hopefully, yes. On Wednesday. Well, today. See, I start saying polyfolds, so we get there. Yes, this all looks very much unlike polyfolds, but it's all the preparation for making real beautiful mathematics by just sort of having one notion of polyfold on SFT spaces. Right. Well, I can give you the upshot now. The upshot is if you have a polyfold description of SFT, then writing things as fiber product immediately gives you polyfold description of all of these things. And that's also sort of part of the trying to identify what the energy and the index are now. So, well, it's been a while, but you don't even really need to remember exactly what the energy on these things was. All you need to remember is that it was some kind of integral of the holomorphic map, U, or the perturbed holomorphic map. So if I think of this as something which consists of pairs of maybe two Morse trajectories and one of these SFT maps you had, the energy is simply going to come in terms of an energy of the U hat. So that's really going to be the Hofer energy then. Key is that there is an energy functional that sits on the SFT moduli spaces, and that gives me my energy. Right? Energy sits in the curves, not in the Morse trajectories. Unfortunately, the index is not that easy. right? So index is a little bit more complicated. We already have, equations here. So index really is more a situation where you have some kind of index of maybe the linearized, and now I'm going to write linearized at the equivalence class secretly because I want to think of subtracting the dimension of the automorphism group, and also possibly this is my index on n, so I might add this +1 simply from the parameter r. Right? And then I need to take my intersections here, so there's a grading at least that this has something to do. P minus, which simply is the dimension of the unstable manifold. Right, and then the P plus comes with the dimension of the stable manifold, but we know what the ambient space has in terms of dimensions, so I get a plus P plus if I subtract the difference 2n minus 1. And so, at least the sort of difference of Morse indices is visible in the index. And that needs to sort of gets combined with the index on the SFT space. I guess what you would expect. So, what's important to note that it's not important is any relationship between the index and the boundary strata. Right? These are sort of different games. And so in particular we can then sort of fix the index and after that look at the boundary strata. So in fact we were fixing the index and the energy. Right. So those are unions of connected components in my moduli spaces because energy and index are both locally constant. And in fact, this lies not just in somewhere in my compactified space, it actually lies in the space that I have from the energy. So it lies in the fiber product that comes from my SFT space where I have energy equal to E0. It's just that if I wanted to also write it in terms of the index k, I would have to take the sort of massive union where it depends, I can have different index here depending on what the dimension is of my, or what unstable and stable manifolds here. Phew. Right, however, eventually our dream is that we can regularize things so that already this SFT moduli space is nice and transversely cut out. And not only that, I'd like it to be transversely cut out, and I'd like it to have transverse evaluation maps to all of these Morse spaces. Because then I could say, all right, if I'm looking at index 0, clearly there's going to be some index additivity. These should be empty when I go to too low index, and then the only way I can get solutions is if that has index 0, and then this has exactly the right index. So that nails down what kind of Morse critical points I can get solutions between. And similarly, in terms of boundary, right? So I could ask myself about boundary, but I want to ask myself about sort of the generic part of the boundary. So I want to take the corners out. Well, I expect that, since I have this fiber product over interior, over a closed manifold, I expect all the boundary to come from the different pieces. And this is 0.4. This is going to have to do with I. Right? I is the one where I just have a sphere. And really these Morse spaces here, let's see, where were we? Right. I is in a case where, right, I didn't say that. Right? There were no buildings in the compactification for I, so we're only expecting Morse breaking. So we only expect boundary times sort of interior of the rest, and then interior times boundary there, with energy still sitting on the SFT thing. And all that I write, so I'm assuming that this n bar here actually has no boundary in corners, and all I did is I went either to the boundary of the Morse space or I took the interior. You can play a similar game for the stretching. Then, right, so your first line is exactly the same thing, simply from the Morse breakings. But now, right, the thing is that this stretch thing, well, you do want to compactify to add nodal curves, but then you'd want the interior of that. So this has, I mean, the stretch thing is going to have boundary, but in these boundary strata, the boundary comes from the Morse thing, so I should take the interior of the SFT space. And then I get 2 extra pieces from the boundary of my SFT space, right? Namely one from r equal to 0, which is, I could have written the same thing here. Oops. Morse trajectory space and then interior, well, boundary of n bar. That has 2 parts, the r equal to 0 part, which is in fact the I moduli space, and the r equal to infinity part. Oops. Right. Which I want to see as these are. I skipped one step here. Right. So the beauty is you can first. You can first think about just the SFT boundary, right? So that has no Morse moduli spaces in it. So that's going to have r equal to 0 and r equal to infinity boundary. So that's no breaking. That was one end of my R parameter, and this is breaking into just 2 levels. Right? Breaking into several levels is going to be corners. So, and with 2 levels, I exactly had these 2 parts of my, the PSS and the SSP sort of part of my symplectic cobordism as I split it. So, right. So that's these, right? And then when I go to the actual M bar, so the fiber product, I'm just going to pick up the extra pieces from the boundary of the fiber product. And hitting this with the fiber product gets me to I. And hitting this product here with the fiber product in beginning and end is beautifully getting me to my PSS spaces. So semi-obvious when you draw it, but it's good to have that really in terms of, well, right now it's sort of expected arguments, but these are going to be arguments that can be made rigorous, on the level of, these being 0 sets of Fredholm sections.
But then your partial M bar also doesn't include the corners.
Yes. Yes. Yeah. Right. So whenever I write partial, I really mean sort of top level boundary. Yeah. I just forgot to say that. explicitly. All right. So that's what we expect, right? So let's see whether we can make that language-wise rigorous one more step. So, all right. So that was the plan of what our moduli spaces are going to be, and now we can go again through this whole algebra. So we need a Morse complex. We're using Novikov coefficients, and we want to define all our maps by counting the index 0 energy fixed parts. Right? And I said the key to that was sort of calling things, representing this as the zero set of a section, where the section here should be index 0. And let me even forget about uniqueness right now. Because really I don't need a unique Floer theory right now. All I need is for some choice of perturbations to prove the Arnold conjecture. Make some choices of maps, and those should factor in the right way to prove how many periodic orbits I have. So, right. And when I say proper, so the definition of proper now is, so the proper definition of proper is to not say that the section as itself is proper, because there are very few proper sections between infinite dimensional spaces. But what we mean when we say proper is that the zero set is compact. Well, actually, sorry. There might be a lot of proper sections between infinite dimensional spaces, but properness does not, as a map, does not imply compactness of the zero set, because the zero set is the pre-image of not zero in a vector space, but the zero section, which, if you have a Banach bundle, the zero section is an infinite dimensional Banach manifold. So its pre-image is not, it's not the pre-image of a compact set. So proper just means that the zero set should be compact. And right, so that proof had two parts. One was to exhibit the moduli space as zero set of a proper section of some type, and then finding some place to cite that says that such sections have a regularization that give you, either a check homology class that you can straight up stick in here and evaluate to get a rational number out, or represent your moduli space after some perturbation as maybe a zero manifold, maybe a branch-weighted zero manifold, which is really just a bunch of points with rational numbers on them. That's something that you could count, but now your choice of perturbation comes in, and you better make sure that for different perturbations, that should be unique up to some kind of the right notion of cobordism that gives you the same rational count at both ends. Right, and I'm writing new underline here because I'm thinking multi-section, which is what gives rise to this branching and weighting, as sort of briefly outlined in finite dimensions. So that was a big black box. I'm going to try and start taking resolutions of that. So here's a little less, maybe a gray box of this. And that's also a little more honesty. So we're not quite going to have the zero set of a section. What we're going to have is our section is going to be some sort of factor between categories. And our moduli space is then going to be the realization. So where I look at the zero set on objects and quotient out whenever there's a morphism. So sometimes that's a safer thing to do than at other times. So what where you want to think of here is maybe, you know, if you were lucky and your moduli space actually was cut out by a Fredholm operator on a Banach manifold, what you want to think of here is B being just the charts for my Banach manifold, and then the transition functions being in the morphisms. Right? So then this is a fairly safe thing to say. Yeah, this is simply the zero set, except it's the zero set in every chart glued together with the transition maps. And so that's the story in all these different approaches. Just you push the subtleties different places depending on what your generating idea is. Right? So the Siebert's kind of global stabilization approach or Euler class approach, right? He wanted B, the space, as a Banach orbifold. Right? And his definition of Banach orbifold was that you have open subsets in Banach spaces that are glued together just with, well, by inclusions, but homeomorphisms, continuous maps. Right? So your object space is, some hopefully maybe finite or at least countable union of open subsets, and your morphisms somehow represented by, or the source and target maps will be local homeomorphisms. And then your sort of bundle category will have very much the same structure, except there's going to be, the fibers will have vector space structure. And just sort of, in terms of differentiability, we don't need to say much else. And so then the only place where Siebert asked for some kind of differentiability was in what this section is, namely on the level of objects. He needed it to be sort of at least locally C1, except for in directions of gluing parameters. We allowed sort of the differential to not exist. But the funny thing really here is that these sort of finite, this C1ness and the finite dimensions here don't need to match up via the transition maps. So that's a neat approach. We can at least locally now talk about the Fredholm index, right? Because if sigma is C1 up to finite dimensions, you can somehow take these finite dimensions out, take the index of the differential in the directions that you have it, and then you should add the finite dimensions. So it makes sense to talk about sigma having a Fredholm index. So, and well, the question is whether that actually is locally constant by this, or even like the same in different charts. Right? So, I don't think that that's a lemma that he proves. You can still try and make sense of the theory. One remark here is that I sort of did in passing. I don't know how clear this is to you guys. I said it makes no sense to start talking about boundaries and corners here. Well, it makes sense to start talking about boundaries. So you could give your open subsets in Banach space. You could ask about open subset in half spaces. But you don't want to start talking about corners versus boundary in this case, because in order to tell a half space from a quadrant, you need differentiability because these are actually homeomorphic sets. So Hofer would say there is no corner recognition, right? Because this point here that looks a little different from the others looks just like any point in there. So don't try. Well, and one might be able to pull through a theory like Siebert's by just saying, well, there's some special points, but they're codimension 1 at least within the boundary. I mean, I don't see a big obstruction in this. But it's not really clear how to talk about it. So new language would be needed. So the polyfold Hofer-Wysotsky-Zehnder approach really is sort of in some sense, takes Siebert and then does sort of the, it likes this whole infinite dimensional approach. But it says instead of going to the minimal possible sort of differentiability that maybe my problem naturally has, and then worrying about how to patch things together, I'm just going to change the notion of differentiability in Banach manifolds and make something exactly so that I can assert that whatever my transition maps were, they essentially write down Siebert's transition maps, and they just say, well, they're not classically smooth, but they're scale smooth, and whatever scale is. So there's a new notion of smoothness, which, both my transition maps and my sections will have to satisfy. And, the object space you want to think of really as Banach manifold in some sense. Which, because I have notions of smoothness now, well, one lemma that they prove is that scale diffeomorphisms do give you corner recognition. So these things are not scale diffeomorphic. That's sort of that's the important test to make sure that it makes sense to talk about boundary and corners. Right. So here's also the first, so the object space here is called an M polyfold, where you want to think of this as manifold flavored polyfold. And really the object space together with this morphism, so then maybe its representative is what you would call the polyfold. It's just like you could build orbifolds as groupoids, right, where the object space are manifolds. So manifolds to orbifolds is like M polyfold to polyfold. So really all that happens is that you have some, transition maps that glue stuff together and some extra finite group actions going on in your morphism spaces. So the morphism spaces, again, are going to be represented by M polyfolds, and there's going to be a notion of diffeomorphism between them. Right, so that's the, one idea is to sort of go in here and say, well, I need a little bit more differentiability. I like the infinite dimensions, I'm just going to change my notion of differentiability. Now, the transverse approach is to say, well, I need more differentiability. If I reduce to finite dimensions, I would have more differentiability. So let me keep my notion of differentiability, but reduce to finite dimensions. So that's really, you would like your transition maps and your section to be smooth. And you achieve that by only allowing your object space to be finite dimensional manifolds. And I say union because they can have different dimension. And so then these also can have boundaries and corners, and you can ask yourself how to glue them together. And the other thing you can ask yourself is whether sort of gluing near nodal curves actually gives you a smooth structure. It probably does for some choice of smooth structure. The natural smooth structure is expected to not actually be smooth. So there's some hope that Dusa and I have that it might be stratified smooth in some sense, and so maybe in some stratified setting you can sort of work with the natural gluing parameters. But this is not a crucial part of the theory. So that's a very big picture understanding of, well, this is your summary of Kuranishi regularization, that's your summary of polyfold regularization. You just need to know what essentially the structure of your categories and your functors is. Well, and then you need to know how to build that. And how to apply it. And so here's the first application, right? So steps 1 and 2 were most complex and making my maps, right? And I was able to make my maps because I was able to write the moduli spaces as 0 sets of index 0 sections. And now I'm going to use things that are index 1 sections. And again, when I say proper, I mean compact 0 set. So, and this is step 4 before step 3 because my I map is a little bit less complicated in terms of what kind of boundaries I expect. So, again, I want to look at index 1 in a very specific energy, which is this nice fiber product. And really now I should write rigorous. This is going to be the representation of the 0 set of my functor. And so how do I want to now cut out a 1 manifold that has the right boundaries to get the, where are we? Here. Right, so this is my goal. I would like an equation that somehow comes from the boundary. Right, this equation says that I is a chain map with respect to the Morse differential, which exactly comes from sort of, I would like the boundary of this to be exactly those and those. So, and I need to do this by giving my base of my section some boundary stratification, and clearly the boundary stratification should come from the Morse spaces. So in the Kuranishi world, I had trouble trying to write this down rigorously. And maybe we'll try to reduce the polyfold setting to that at some point. So here's, in polyfold world, this is really nicely written out. Because I need to tell you what the polyfold is. What is the base of my section? And you might think that now I need to actually tell you what a polyfold is, but I'm not going to. I'm just going to say if you have one polyfold, B sub n, that gives you, the SFT moduli spaces. Oh, and this is going to be a lie. Then this fiber product here is again going to be a polyfold. And that's the total lie. Let me correct that lie. I'm not going to take the fiber product, I'm going to take the Cartesian product. Whatever a polyfold is, if I take a Cartesian product with finite dimensional manifolds, it's still a polyfold. Except I've now removed the fiber product, so I need to encode that someplace. I'm going to push it into my section. So my section of a triple now is going to be the d-bar operator together with some evaluation maps coinciding. So I would like sort of f of x minus, well, to be equal to some evaluation map of u hat. And since I want this to be a section, there needs to be a minus sign in some local coordinates. And the same thing with x plus. So 2 different evaluation maps written so squiggly that you can't tell them apart. And you would now think that I need to tell you what polyfold Fredholm means, but I'm not going to. I'm just going to say that my d-bar operator, if I can prove that that's polyfold Fredholm, then this map is going to be polyfold Fredholm. Because all that it is, it's a Fredholm map together with some differences of smooth maps in that live, map from finite dimensions to finite dimensions. Clearly, that's not going to affect the fact that it's Fredholm. It's going to affect the Fredholm index, but that's fine. So these are conditions on the notion of polyfold. But now the neat thing is my SFT moduli space was supposed to not have boundary, right? Because they're just holomorphic spheres. So they only have nodes, those are interior points. That means when I think about boundary, I'm expecting, oh boy, I guess, oh, that moved down here, right, oops. Oh, I don't have that. Right, so the boundary now of this is going to be coming from boundary here and boundary there. So it's going to be boundary of this plus that with the boundary of this Morse trajectory space. And so that informs me for, to start with, I can understand, well, if my moduli space by itself was very, very singular, I can't tell you what its boundary is. Topological spaces don't have boundary by themselves. But I can tell you where I'm hitting the boundary of my ambient space when cutting it out. So that's exactly where I hit these bits. So the boundary of this Morse moduli space and the interior there, or the boundary of that Morse moduli space, where, the nice thing is we've constructed them so that this boundary is exactly, now I should take the interior here. So, product of unstable or stable manifold with once broken thing. But these here are exactly my my Morse trajectories now, and this is part of my fiber product that gives me back my PSS moduli space. So this, I break things differently to get back into some union of I, and then that broken off curve goes here. Same thing in the first factor. That's this, and that is here. Okay, but now let's see. So now I need to look at how my index shakes out. So sort of cheated a little. So my index additivity now is index 1 here. That's going to come from expected dimension of this Morse moduli space plus that one. Right, yes, because my coincidence conditions were put into this moduli space here. So, 1 should be the sum of this plus that index of here, same way. Well, one thing I know is that my Morse trajectory spaces are empty unless that index difference is at least 1. So that forces k here to be 0 or less. And so now comes the trick where I would like to regularize this whole problem so that index 0 so that index negative moduli spaces are empty. So I'd like that force to be bigger or equal to 0, because then this is index 1, and that is exactly the differential for the Morse trajectories. And this is then I. So this is equal to 1, then this is the differential, and this is equal to 0, then it's I. So the claim here is that when I regularize, within this some notion of section, I would like to get a compact, weighted, branched manifold out, you know, presumably from some kind of multi-valued perturbations, taking the zero set and then taking the representation in my category. Right? So that's going to be the regularize. So regularizing here happens with the superscript reg, and that comes from nu. And just like in finite dimensions, I expect to get the boundary of the perturbed thing from the solution set intersected with the boundary. And so, since I've written my equation now in the polyfold world, right, I've already written it in terms of Morse trajectories and somehow. If I perturb this, I'm going to perturb the d-bar equation. I'm also going to perturb these coincidence conditions, but I'm not going to perturb the fact that x minus and x plus are Morse trajectories. And so that's where, the whole argument up there, where I had some wishful thinking to say that, should be empty set unless the index is positive, is going to be rigorously true in this world where these regularized moduli spaces are simply these perturbed zero sets. And so these will now actually be empty. Unless they have index positive. And so, well, right, that's what forces this index difference being 1. So, that's where the equation then comes out. You need some notion of cobordisms between weighted zero manifolds that tells you that the rational numbers that you get out of counting both ends are, add up to 0. So that's what sort of goes into this deduction here. So since that was complicated enough, I'm leaving the harder equation, right, with 4 types of boundary components as exercise. But really, it's exactly the same kind of story, where you just need to write your H PSS moduli space as 0 set in an index 1 situation, and the regularized boundary should be, again, the intersection with the boundary of your polyfold, except that now the polyfold is going to have, Morse breaking on the boundary together with, these are then sort of boundaries of my SFT polyfold, the N. So that's going to have 2 boundary parts, simply r equal to 0 and r equal to infinity. That's going to be 2 buildings, you can build that whole ambient space and we'll try to do some part of it. Okay. So really this is all an exercise in kind of saying the things that you were used to saying, except saying them in the language in which that is not just mumbling but is rigorous math. So we're going to try and develop more of that language. So, this was, well, now we're essentially in a setting where I just need to tell you what a polyfold is so that this is the correct language.